Okay, so let's start. Last time we talked about how to determine local extremality using the Hessian. So let me review briefly the essence of this method. So this is our theorem. So when you have a two-variable function and x0, y0 is a critical point, we want to determine whether it's local maximum or minimum or saddle, and sometimes you cannot determine the type of this critical point, but that's done by looking at two values. One is the discriminant of the function, which is the determinant of Hessian, and the other one is the second order derivative fxx. Okay, so when we explain the reason why this theorem works, we introduce two types of transformation. One is the linear translation, so simply translate your point x0, y0 to the 0, 0 origin point, and the other transformation is a linear transformation. That's a general transformation that does not involve the linear translation. So the type of translation in this specific proof is this one. It's kind of related to rotation and dilation around the origin. So I will show you what happens when I translate my axis, transform my axis by rotation and diagonal and to the shape of the graph. So here's our MATLAB code that I'm already wrote here. So when we have this kind of function, this is a monkey saddle. We saw this, for example, in 2 weeks ago. So we have two surfaces. So in the between, I have this subplot command. This 1 to 1 means that there are 1 row, 2 column, and the following graphing command will plot the graph in the first graph, first plot, first figure, whatever. And there's a subplot 1 to 2. The same thing here is 1 row, 2 column. This is the second picture. Okay, so the first picture is drawing this graph of function in original way. So from -1 to 1 for x and y axis, I'm drawing the monkey saddle. But for the second plot, I'm going to translate or transform my axis x and y to xx and yy in this way. So I'm trying to be similar to the form that we used in the proof of the Hesse theorem, and see what happens. So I'm going to dock here. So the picture on the left is original monkey saddle, and picture on the right, I made the two axes to be equal here. It's -1 to 1, -1 to 1. So what happens is it a little bit squeezed, and also it was rotated. Okay, so maybe the picture looks like this, a little bit like this, a little bit rotated, and it was squeezed. Okay, so entire area here is squeezed by how much? Like I think around about y-axis, maybe even on x-axis it was squeezed. 조금 끊겼네요. 네, 다시 들어왔어요. Okay, let me explain again. So, okay, so the left picture is the original, our saddle point, the monkey saddle, and the right one is the result of linear transformation using these equations. So it was rotated and squeezed a little bit, And the important point is that when you're looking at the 0, 0 on the original graph, it is translated to the 0, 0, the same origin point on the squeezed picture, right? So when x, y are 0, 0, and then the double x and double y are also 0 by this equation here, right? But the type of that critical point, so it's still the saddle point. So it was saddle point on the monkey saddle here. So it's not local minimum or nor local maximum, but the tangent plane is flat. Same thing for here. So if you kind of zoom in here, it's still a saddle point if you're looking at the 0, 0 point here. Okay, it's not changing its nature. So that's why we're okay to use only the discriminant and the second derivative of functions. So from now on, we are going to use that theorem to apply many practical examples. One of them is the least square method. So this least square method is used to find the regression line for data points. Regression is 회기선. 회기선을 만들려고 하는 거예요. 지금 데이터가 주어졌을 때 회기선을 찾는 거. So how do we choose such a line? So in order to find the line, we need to find the y-intercept and the slope, right? So basically we want the equation of a line, and we need to determine m and b. So m is the slope and b is y-intercept. How do we find the best line that fits the data? So there are many ways geometrically, but the common way and most easiest way is to find the line that minimize the error terms, right? And not just the sum of the error term goes to zero, it goes to minimum. I want the square of the square of the error term goes to minimum. So what I'm trying to imagine is, suppose that I'm choosing my line as my estimation of this function. So assuming that this data are given by some unknown function f, and assuming that this f is linear, then I'm guessing that this function has the formula like mx plus b. So these yi are actual value, the actual value, and my estimate f of xi, which is y prime, estimate. So sometimes the word is opposite. So yi is not a, so this is an estimate, sorry, and this is actual value. The reason why yi is called actual estimate is called, we are assuming that this data actually follows the linear line, but because of other other error noises or other outside reasons, this actual value are obtained with the errors. So we call this yi, which is which is the result of observation, as an estimate, and our value of the function, which is approximated by the linear function, is the actual value, which should be obtained if there is no error at all. So I want to find the MB which fits the best to the estimate. The way we do is that the difference between the estimate and the actual value has the least square sum. So we have a subtraction between two values and then take the square. So therefore all of its squares are positive, and we want this sum of positive numbers to be small as possible, as small as possible. Okay. So what we want to find is, I want to find the value m and b, which makes this entire formula in terms of m and b to be minimum. Okay, so I will call this formula just as a function called d. Okay, so instead of m and b, all the data, all the values yi and xi are given. So in this formula, it seems like xi, y are just variable, but it's not. It's a number already given, so it's simply a function of m and b. So more simplified version is that this is simply a two-variable function on m and b. So forget about all the formula. Just think about the Hessian again, the Hess's theorem. So in order to find the local minimum or local maximum, first you need to find a critical point, and then try to compare the discriminant and the second derivatives. Alright, so what's the critical point? It needs some work here, so let me add another page. Alright, so we have d and b equals to yi squared minus 2 mxi plus b yi plus mxi plus b squared. So this is yi squared, so this is constant, and minus 2b yi, also that's a constant, and minus 2m y, oh sorry, that's not constant, so let me put this b at the end. So this is the coefficient of b, and here we have 2 times y and xi, right? And that's the coefficient of m, and that's a linear terms so far. So and then we have the sum of xi square as coefficient of m square, and 2 times xi and b, and last one is n times b square. Okay, so this part becomes this part, and this part, for example, becomes this part, and so on. Okay, so let's try to find the critical points. Let's say I'm taking a partial derivative of d in terms of m. Then what we have here is minus 2 yi xi times and plus 2 xi square m, and we have 2 xib. Okay, that's one thing. I want this to be 0 at the critical point. By the way, there are no type 2 or type 3 critical points, because type 2 means that it's partial derivative will not exist, and 3 means that it's not continuous. But these are polynomial on m and b, so there are no type 2 to 3 critical points. So we only want to find the type 1 critical point, and db is minus 2 yi and plus 2 xi and m. Sorry, wait, this is m, this is b, sorry. then I have 2nb. Wait, I'm sorry, I made a mistake here. So this is m. Sorry, this comes from here. Okay. All right, I want this to be 0. So this kind looks very long, but let me rewrite this into matrix formation. So this becomes, so if I take these parts to the right hand side here, this becomes 2 times xi square m plus 2 times xi b equals to 2 of yi xi, and now this is 2 times xi m plus 2nb equals to 2 times yi. So I can rewrite this as mb times 2xi squared 2xi 2xi 2n equals 2 yixi yi 2 times. So there are 2 everywhere, so let me erase these 2. So this 2 disappears, so let me erase all the 2's here. And okay, so I want to solve this metric equation in terms of m and v. Now, do you remember the Cramer's rule in the differential equations course? So easy way to find such m and b is that m is the determinant of, let's say this is the matrix A. So I can find my m as determinant of A and determinant of A whose first column replaced by the last one B here. So instead of these 2 elements in the first column, I put xi, yi, and xin. Okay, so these columns follow from here. Okay. So what happens here? We have n xi square minus xi square, and then we have n yi xi minus xi yi. Okay, that's our m. That makes this 2 equation hold. Okay, so that's our formula I wrote here. So this is the critical point, only one critical point in this case. Okay, so you can do the similar for b. So you get this 2 solutions. Okay, so let's try to think about the Hessian here. So we had this 2 formula for first order differential derivative. If you take the further derivative, dmm becomes this guy. So here, dmm is here, dmb is here, and dbb is 2n. So the Hessian looks like this. Okay, so let's compute the discriminant. So discriminant is the determinant of this 2 by 2 matrix, so it becomes this formula. Okay, now y, this is always positive. Why? Let's think about y here. So here we have, let me make another page here. So let's copy this formula. Well, I don't need 4 here, right? So let's take this 4 out. So we have n xi square minus xi square. Okay. So the problem is here. We have a square of the sum, not sum of squares. So n times xi squared minus, now this becomes xi squared plus 2 times xi xj, where I and j are not equal. If it's equal, it becomes a square. Okay. So we have n minus 1 of xi squared and minus of 2 times ij not equal xi xj. Now I can group them again using for each pair of xi where I and j are not equal. For each I and j, well, let's say not just not equal, let's say I is bigger than j, I can group them as xi squared minus 2xi xj. Oh, by the way, so sorry, so this is, there's no 2 here, because when I write 2, I mean xi xj and xj xi, so that's included when I put I not equals to j. So when I put 2, I'm putting an order of I and j, so let's say I is always bigger than j. Okay. And xj, so I'm grouping for each pair of ij where I is strictly bigger than j. I take 2 squares from the first summand here, and then take minus 2xi xj. So then I have xi minus xj squared, and sum of squares is always positive. Okay. By doing this, I exhaust all of the n minus 1 times of square sum. Okay, you can check by yourself. So this is always positive. Maybe I don't need this page then. So just let me copy this one here. Okay. I'm going to erase this page. All right, and how about this DMM? So DMM was right here, this one, 2xi squared, and also it's positive. So we have positive discriminant and positive second order partial derivative. That means the critical point is local minimum. Okay, so we found that m0 and b0 is the slope and y-intercept of the regression line, which minimize the sum of square of the errors of the actual value. Okay, we can say that this is the actual minimum, global minimum. Why? Because this m and b, this d of mb is defined on the entire plane on m and b. Okay, and we found that there are only one critical point. So there are only one possibility at one point that this could be a local minimum or global minimum. If it's a global minimum, obviously it's a local minimum. So we have only one candidate to be a global minimum, which is this point. So there are no other local minimum. Okay. So this is extremely useful also in many calculations. I mean, like a MATLAB calculating program, they have a command that finds a regression line of the given data sets. Okay, but you can also do by yourself. You can write your own regression, own program, own function, which outputs the regression line only by taking this formula of the slope and the y-intercept. Okay. And let me finish by remark here. So what does it this regression line do is taking the errors between the line and the point, but you have to be careful what kind of line is that in this picture. So we have we have x-axis here, and y-axis here, we are looking at the error represented by the line which is parallel to y-axis and perpendicular to x-axis, and taking all the square of these lengths between this point and the line. This is not the distance between point and the line. If you want to find the distance, it should be perpendicular to the line, right? So if you really want to find the distance, you have to take the length of the blue lines. But in this regression, we're taking the distance, the length of the red lines. Okay. So the regression, takes the red lines length of as the error. Okay, not the blue one. Okay, you can take the blue one as an error. That's another type of regression that will be considered in the linear algebra course in next year. However, for now we are only taking the red line as a linear line. We are just looking at the difference between the y-axis, not considering the how much x-axis difference. X is an input, so I don't change the input. I only see the how much the output was differ from the actual value. Okay, so this is x1, x2, and so on. Okay, be careful about that. And let's also apply this kind of Hessian to the 3-variable function case. So you can also find a critical point for 3-variable function by taking the partial derivative fx and fy and fz, and then find the point x0, y0, z0 such that these 3 partial derivatives are all 0. That's the type 1 critical point. You can also find the type 2 critical point using the same definition, saying that if one of these partial derivative does not exist at some point, that's a type 2 critical point, and if function is not continuous at that point, that's a type 3 critical point. But let's forget about type 2, 3. We only think about polynomial or other well-defined functions such as exponential functions and so on. So there are no discontinuous point or no partial derivatives any point. So let's say we are going to define a Hessian as a 3x3 matrix, consists of following. So we have fxx, fyy, fzz consists of diagonal entries here, and it's symmetric, meaning that the row and columns are switched, then but even if the row and columns are switched, you get the same matrix. So we have xy on first column, first row, second column entry. We have fyx on the second row, first column entry, but these two are the same because we are assuming that this function has continuous second order partial derivative. Okay, so when we use this kind of method, we always assume that this function is function has continuous higher order derivatives. Okay. So then, how do we determine the local minimum, local maximum, or neither of that? So we are going to define d1, d2, d3 as follows. So d1 is the determinant of the top left corner of 1 by 1 matrix. So this is d1. And d2 is 2 by 2, determinant of 2 by 2 matrix on the top left corner of the 3 by 3 matrix. Okay, and d3 is the entire determinant of the entire matrix here. Okay, so sequentially you take the determinant. Okay, so that's called also the discriminant of the minors, but let's just call it determinant. And the result is that if all three DIs are positive, then that point x0, y0, z0 is local minimum. If the sign of d1, d2, d3 are alternating, starting from negative, which means a negative, positive, negative, so this is d1, this is d2, and this is d3, then that's local maximum. So now it's not like the second variable functions, right? So it's a little bit different. So in all other case, if d1, d2, d3 are not of this type, first type or second type, then this point x0, y0, z0 is a saddle point. So I'm not saying this point looks like a saddle in this saddle, the monkey saddle, or like a saddle graph of the surface. The saddle point means that it's a critical point which is not local minimum or maximum. In other words, there are paths makes this point to be locally minimum on that path, but the other path makes this point local max and local minimum. Did I say minimum first? Okay, so there are two passes. If the point is saddle, there are two passes such that on one passes, this point is local minimum on the path, okay? And on the other path, this point is local maximum on that path. That means if I look globally on this graph, I cannot determine whether this is locally minimum or locally maximum. Let me explain by this MATLAB here. So I already made a code here. We have this kind of picture, x squared, y squared, z squared here. So this point at this graph has 0, 0, 0 as a critical point, obviously, because fx is 2x, fy is 2y, fz is 2z. So only way we have all zero partial derivative is when x, y, z are all equals to 0. And that's the only critical point we can get from this function. And this is a 3-variable function. You cannot draw, like in a 2-variable function case, your function of 3-variable function in 4-dimensional graph, 4-dimensional plane, because simply we cannot visualize a 4-dimensional space. There are ways you can draw in the MATLAB up to 4-variable and 3-variable function. The way the MATLAB draw this kind of function, so let me erase this figure, is using the color. Okay, so you see the 3-variable function has the domain of 3-dimensional space. So if you pick any points in the 3-dimensional space, that becomes the input of the function. Okay, so originally this domain should be filled entirely, fills entire 3-dimensional space, but we are taking a section in 3 different directions and then see the value of function by the color. So here we have, I put the color bar option command here. So on the right side of the graph, we have a color with this index points, like numbers here, inside a 4-dimensional space. 자꾸만 끊기네, 뭐야. 또 끊겼죠? 지금은 또 괜찮은데 중간에 잠깐 끊겼네요. So let me explain again. So this is the way how MATLAB draws the shows you the kind of graph of the variable function, but this is not actual graph of the three variable function. So how MATLAB depicts this three variable function is using the color as the value of the function. So this is the sections on the domain of three variable function. Okay, so I put the sections as a planes perpendicular to x, y, and y, z, and x, z planes, and then I depict the value of function as a color. So when I put the most blue point is the 0, represents 0, and the bright yellow represents number 3. Okay, so on the 0, 0, we have the most blue color here, so it means that the value of function is 0. So it doesn't actually shows you exact value, but it kind of give an intuition how large the value of function is by using the color. And when the point moves away from the 0, 0, 0, then its color becomes the greenish to the yellowish again. So when the color is greenish, then the value value approaches to 2 to 3, right? 0 to 2 and 3. So I didn't put the larger peak figure here, so there are no value of 3, but maybe the value approaches to 2. But anyway, the 0, 0, 0 is the most smallest, has the most smallest value of a function, which is 0. All the other points around 0 cannot be larger than 0, 0, 0, right? However, if I take a different formula here, let's say take a minus signs all the way here. What happens is that at 0, 0, 0, it has the largest value 0, okay? And when it moves away from 0, 0, 0, the value becomes -2 because it kind of moves like becomes bluish point. Okay, so when it becomes blue greenish, then it becomes a negative value, right? So let's compare these two type of functions and into Hessians. So this is the simplest one. So when I have f equals to x squared, y squared, and z squared, then Hessian is 2, 2, 2, 0, 0, 0, 0, right? So that means d1 is 2, d2 is 4, and d3 is 8. They are all positive. So it's the first case. So when di are all positive, then it's local minimum. That's what we saw in the first graph. And what if we have f as minus x squared, minus y squared, minus z squared? The Hessian becomes minus 2, minus 2, minus 2, 0, 0, 0, 0. So d1 is minus 2. And what about d2? d2 is the determinant of this 2 by 2 matrix. So it's 4. It's plus 4. And what about d3? It's again minus 8. So sign alternates, minus, plus, minus. That's the case when we have a local maximum. Okay. So what if we have a function like x squared minus y squared minus z squared or plus z squared? So what's the Hessian? So we have 2 minus 2, 2. So then d1 is 2, d2 is minus 4. What about d3? It's still minus 8. So sign doesn't alternate, or neither it's all positive. So in that case, that's the case 3. This is called a saddle point. So how does a saddle point and the 3 variable function look like? Let's draw it in the graph, in the MATLAB. So here I have x minus y squared and plus z squared. So that's the graph. So at 0, 0, 0, its value is somewhere like maybe 0.5, okay? It should be 0. It should be 0, so it should be 0 here. And now this is the important point. When I move my point away along this plane, okay, so this plane, the value of function becomes 2, so it becomes larger. So on this path, on this plane perpendicular to y-axis, this 0, 0, 0 is the local minimum. Okay. However, if I move my point 0, 0, 0 away from this line, then the value of function becomes smaller to the -1, right? So this 0, 0 is local maximum. So depending on the path I'm moving my point, this point could be local maximum, local maximum or local minimum on that path. So when I look this global domain of the function, then the point is neither minimum or maximum locally. There are always a point near that 0, 0, 0, whose value of function is greater than 0, 0, 0 or smaller than 0, 0, 0. So that's called the saddle point, a critical point which is not local nor minimum, not local minimum nor maximum. Okay. So if you see the kind of the patterns here, you can generalize the Hessian, the method of Hessian to n variable functions. So this is for 3 variable function. What if we have 4 variable functions? Of course, now there's no way we can depict the behavior of function for 4 variable function, but you can determine the type of the critical point using the similar method in Hessian. So you take the Hessian as 4x4 matrix, and you're looking at the top left corner of matrices, and then take the determinant and set it as d1, d2, d3, d4. And if all these di's are positive, then the critical point is local minimum. And if the sign of di's are alternating, starting from negative, then the critical point is locally maximum. Not going to talk about that right now, but just telling you by words how you can do it when you have n variable function. And all the other cases, it doesn't follow the first 2 cases, then this point is settled. All right. So far that was the example of that was the example of the Hessian. Okay. And now we have a different situation. So we are going to talk about the Lagrange multiplier, which is the highlight of our multivariable calculus. And also it's a very nice example, application on chain rule. So before we dive into that subject, I will wait for a question. If you have any question, please ask right now about the previous material, any other material. No questions? Okay. So in case we so we have one questions. A nice analogy. So the question is, so we can't draw the graph of 3 variable function as if its graph is a graph of a two variable function, but graph of a three variable function. Looks like already, what is it called? Something like the camera, night vision camera. Yeah, right. So right, that kind of camera, you remember the camera, I forgot the name, but the camera that people puts on the entrance door of the hospital, especially for this kind of situation. Yeah, infrared camera, right? Right, that kind of camera show you the temperature of the human, or temperature of the object in colors, right? Right. So yeah, if you think about your human body or two-dimensional human body as a function in two variable, one is the xy, three variable, for example, like you have a position of your body as x and y coordinate, and the temperature of that point on your body as the third coordinate of the input of the three variable function. Then this infrared camera shows you the graph of function, right? This very nice analogy. I buy that. I'll buy that. All right. Let me search for a problem that we can solve here, in case that we don't finish this entire slide today. So problem is find all critical points and classify them of these two functions. For example, this one has type 3 critical points. So whenever x coordinates are 0 and we have any y coordinates, or any x coordinate x0 and 0 is y coordinates, these are critical points because this point is not a continuous point of this function. So forget about these critical points. We already classified as type 3. What we want is if this critical point, if the critical point is of type 1, classify the extremality of that critical point. So let's find out a point which is not containing 0 as a coordinate, but whose fx, which is y plus x minus x squared 2 and fy equals to x y squared 2 becomes all 0. Let's see whether MATLAB can do this problem for me. So here I'm going to define symbolic variable x and y. My function xy is x times y, 2 over x plus 2 over y, and fx is diff fx, fy is diff fy, and my equation is two things: fx equals to 0 and phi equals to 0. So I'm going to solve equation and store that as sol, and I want to find sol x and sol y. What's wrong here? 2 over x plus 2 over y, same as xy, fxy Okay, so maybe the problem arises because I use f as a name for this kind of functions, but I also use this as another function. So I cleared every variable that's stored previously. So clear all does that. So you can do this clear f. So it has, okay, that's kind of complicated. So it seems like we have two complex number which satisfies these two equations. We don't need complex number. We only want the real numbers. So we have third root of 2 as x and y as the critical point. So we have one critical point in xy plane. So you can classify them using the Hessian, and you can do the similar for the second problem. Okay. So how about okay, so from now on we have Lagrange multiplier. Right, so let's do the Lagrange multiplier. All right, so here we're going to look at first proposition first. So do you remember the level set LCF? So level set LCF is defined to be the set of points where value of function equals to C. So level set at C of the function. Okay. So remember that this function is two variable function, for example, and the level set is lying inside of two-dimensional plane. Okay. Usually it's a curve. Okay. And then the gradient vector, this is again fx x0 y0 fy x0 y0 two-dimensional vector. Okay, so we have two-dimensional curve, which is the level set inside of xy plane, and also we have two-dimensional vector that we can put on this two-dimensional plane, xy plane. The proposition says that this two-dimensional vector is always perpendicular to the curve at the point. So for example, we have level curve inside of two-dimensional plane. Let's say we have point x0 y0, and we can think about the tangent line on this graph, on this curve. The gradient vector is at this point is always perpendicular to this tangent line, this f of x0 y0. Okay. Okay, so the proof is easy, so let's write the proof here. So let's say CT, which is xt, yt, be a curve in CLCF. Okay, so I'm going to parameterize my level set, which is level curve inside of two-dimensional plane, as CT. But if f is not two variable function but higher variable function, then you can think about a curve actually lying inside of this higher dimensional level set. Anyway, if I take the composition f and c, that's a function of t, that means I'm taking a point xy which lies in the level set. Therefore, by definition, the value of function is always the constant c. Sorry that I used the c for the name of parameterization and also the value of function. So let me put it as d. D. So this is constant. So if I take the chain rule on the left hand side, fd prime, okay, by the way, such that this d0 is x0 y0. Okay, so I'm going to take a derivative at 0, That means by the chain rule, I have fx x0 y0, which is d0. Let me just put it as d0 here. d0 times x prime 0 plus fy d0 times y prime 0 to be equal to 0, because on the right hand side I'm taking a derivative of a constant, right? So it means that this is equals to the gradient of f at x0 y0 inner product with d prime 0 at d prime 0 is 0. So this is inner product, right? So you have two vectors. One is gradient and the other is the velocity vector of the parameterization, and these two vectors are perpendicular to each other because their inner product is 0. So therefore we're done. This is very important in the Lagrange multiplier that we are going to explain now. So our assumption is that we have two functions, f and g. So f, later we will call this f as a target function. Okay. And we assume that these two functions are differentiable functions, which means that it has continuous, or for example, it has continuous partial derivative. Okay. We're going to define a level set of g at the point at the value c. Okay, so think about this level set. We will call this constraints. Constraints, not s. So basically we have target function and constraints. That's the two ingredients to the Lagrange multiplier. Now, if x0 and y0 is an extremal point of this function on this level set, oh, there's an important condition missing, on the level set LCG, and the gradient vector of the g at the x0 y0 is not 0, then there exists lambda such that these two vectors are satisfying this equation, which means basically that this f and g, the gradient of f and gradient of g, are parallel. Okay. So this is a theorem. This is not really a method. It just tells you why the Lagrange multiplier works. Let me explain actual Lagrange multiplier method here. Here I'm going to take another page. So objective is that we want to find a point x0 y0 on this constraint such that f of x0 y0 is locally minimum or maximum on this LCG. So we are going to restrict our domain of f on this level set. So let's say we have a function defined on R2. So the value of function is real number. We're not looking at the entire domain, entire R2. We are only looking at the constraints. Let's say this constraint is the level set, so like a curve here. So this LCG. So important remark is that we want to find local extremals on the LCG not on entire R2. Okay, so in other words, restrict your domain of your function f to the level set of the function of g. Okay, so I will explain why this kind of setup is useful in the practice. So then what we have to do is to find first, check this f and g are differentiable at and then find these two gradient vectors. So actually this is the vector field, because I don't pick a specific point to calculate my gradient vectors, so this is actually vector fields. So this is a function of x and y still. Find x, y, and lambda satisfying this g lambda. Lambda comes in g part. Okay, sorry, doesn't matter actually. I can put lambda on the x part, and this g x y equals to c. So we have two set of equations to solve. One is the equation on the vectors, and the other is the equation on this graph g, a value of g. Okay, so the conclusion is, if x and y satisfies this equation, then such x0, y0 is a candidate of local minimum or maximum of function restricted on this level set G. Why? So this theorem tells you that if it's an extremal, then it should be, these two gradient vectors are parallel. So actual method is going backward. Let's try to find all the points whose two gradient vectors are parallel. Then it could be an extremal. It does not guarantee that it is extremal, because this is simply a converse of this theorem, but it could be an extremal, so we can have a nice candidate to check whether it is actually an extremal of the function. So let's look at examples here. Let's try to find the local extremality of the function defined to be 3x plus y on the constraints x squared plus y squared equals to 10. So here we have gxy equals to x squared plus y squared, and this is our function f. First, check whether f and g are both differentiable. These are polynomials. Obviously, it's differentiable. It's infinitely differentiable. Okay. And second, try to find the x, y, and lambda, which satisfies del f, which is 3, 1 equals to lambda of 2x, 2y. That's lambda gradient g. And what? X squared plus y squared equals to 10. I want to find x, y, and lambda. So here x is looking at these two equations. So actually there are two equations, right? So 3 equals to lambda 2x. So therefore x can be written as 3 over 2 lambda, and y is 1 over 2 lambda, right? And then plug into these equations, and we have 4 lambda squared 10 equals to 10, therefore lambda could be plus minus 1 over 2. So if lambda is plus 1 over 2, then xy is 3, 1, right? And if lambda is minus 1 over 2, then xy is minus 3, minus 1. So we have found a candidate 3, 1 and minus 3, minus 1 that could be a local minimum or local maximum of the point of the function f restricted on the circle, right? So let's look at that in the MATLAB here. So okay, is that this? Oh, this one is not. Okay, so let's first draw the graph of function f. I have to clear all xy. Fy is 3 times x plus y, and g as xy is x squared plus dot square y dot square, and xy equals mesh grid. Let's say here, because at least I have to put this circle of radius square root of 10 inside, so my point should be at least minus 3 to 3. Okay, and then surf xy and fxy. Let's say x is equal. Okay. So you see, actually what you can expect is that this is the graph of some plane. So we have a graph of plane. I'm not going to graph the graph of G. So G is used to define the constraints. We're not going to use the graph of G. However, let's draw the constraints here. So hold on. And when I draw the contour, not the contour, implicit, sorry. I want to draw f implicit. The graph of G equals to some value C, in this case 10. So I have to draw the implicit graph of implicit function. So I'm using f implicit, which draws the implicit graph of xy, g xy minus 10. Okay, hold off. Okay, so f implicit plot. Forget, I saw my implicit. Okay, so it's hiding here. So okay, so you can see this implicit graph here, and this implicit function graph is lying inside of xy plane. Okay, so I'm graphing the level set here. So this level set lies inside of xy plane. So that's why it kind of lies on z equals 0 plane here. That's xy plane here. Okay. So I know that this is actually a circle. So I can reparameterize this circle as theta. So theta is linear space from 2 to 2 pi, 0 to 2 pi. And let's draw this. Let's draw the graph of function restricted on these constraints. So the actual domain of the function is entire R2 plane. Okay, so it's a surface, but I'm going to graph the function whose domain is restricted on these constraints of level set G, right? So I'm only graph this value of function lying on top of this circular line, the blue line here. Okay, Let me put the line width. It's 2. Like make it thicker, or maybe okay, leave it as a blue one. So plot 3 x cosine 3 times square 10, sorry, so square 10 cosine theta and square 10 sine theta. That's x and y, and graph the value of function. Sorry. Graph the value of function f of square root 10 times cosine theta square root 10 times sine theta. And let's take it as red line and line width as 2. What's wrong in here? 92. F of, I forgot here. Okay. Line width. All right. Why does this become the red one? So anyway, let's make it larger. So minus x axis minus 3 to 3 to minus 10 minus 15 to 15 minus 3 to 3 and minus 15 to 15. Okay, let's equal there. Alright, that's so somehow I think it's because of the f implicit. The graph doesn't, this x the x boundary and y boundary doesn't get larger than minus 2 to 2, but anyway, you see what I'm saying here. So we have a graph of the function, original function, and we have a graph of function restricted on the domain of blue line here, right? So I want to find the local extremals of the red ones. So red one is the graph of the function restricted on the domain of constraints. Okay, so extremal happens on this top and bottom here. So somewhere on here there is a local maximality, and somewhere here there is a local minimality. What we found in our slide is 3,1 and minus 3, minus 1. That's the two possibility of local extremals, right? So you can imagine that 3,1 is the local maximum, and minus 3, minus 1 is local minimum. It's obvious because if you put 3,1 and minus 3, minus 1 into the function f, the value of function becomes positive and negative. So the larger one is local maximum, the smaller one is local minimum, and so on. So that's how you find the local extremal of the constraints, the function restricted on the constraints. So let's look at other examples, and then when we are comfortable using this Lagrange multiplier, I will explain why this kind of method works to find the local extremals. This is hard ones. Let's look at the examples here. So find local extremal of this given function with the constraints this. I will do the first one, you can do the second one by yourself. So here first, you can, by looking at eyeballing, that this f and g is a 2x plus y square, are all differentiable, so I don't need to check the first one. First, take this gradient of f, which is 2 plus 2x and 2y. I want that equals to lambda gradient of g, which is lambda 4x 2y, right? That's one equation, and I want x and y satisfying this equation and the constraints. So rewrite this equation: 2 plus 2x equals to 4 lambda x, and 2y equals to 2 lambda y. So possibility of the second equation is that I can remove 2. So either lambda equals to 1 or y equals to 0. That's the only possibility we have. So if lambda equals to 1, then on the first equation, let's also change this to 2. Then what we have is 1 plus x equals to 2x. So therefore x equals to 1, right? If y equals to 0, that means lambda can be anything. Then our equation is 1 plus x equals to 2 lambda x. Therefore x is 2 lambda minus 1, 1, right? And then, so let's summarize. We have a possibility that x is 1 and y could be anything, so let's leave it at y. I don't know what y is yet, but lambda is 1. Or if y is 0, I don't know what lambda could be, but x is 1 over 2 lambda minus 1. That's the second possibility. So let's plug that 2 possible points into the constraints. So if I put this into constraints, here is 2 plus y squared equals to 2. So therefore y should be 0, right? This is simple. So if I take the second possibilities, then we have 1 over 2 lambda minus 1 squared and 0 squared. That should be equals to 2. So therefore this 2 cancels out. We have 2 lambda minus 1 must be equals to plus minus 1, right? So this lambda is 1 over 2 times 1 plus minus 1. So it's either 1 or 0, right? Both make sense, right? So what we have here, can I write here? Okay, let me keep writing here. So we have 1, 0, 1 as one possible candidate for local extremal. And the other candidate is when lambda is 0, we have minus 1, 0, 0. Well, let's forget about 0. I just want xy coordinates, so just forget about 0. Lambda parts. And when lambda equals to 1, I have 1, 0. Oh, I get the same thing here again. So I can just think about these 2 points, right, as a candidate for local extremality. So how do we determine whether it is local minimum or local maximum without graph the function? So best way is just graph the function again, but if you cannot graph it, then plug these 2 points into the function. So look at the value of function at 1, 0. The value becomes 3, right? 3. And what about minus 1, 0? Minus 1, 0 becomes minus 1, right? Yeah. So this is bigger and this is smaller. So we know that this is local maximum and this is local minimum. Okay. Well, let's draw this. check actually what we have done is correct. So, all right, so let's look at the constraints here. So look at constraints here. This is a parabola. So I can rewrite this as x squared plus y squared over 2 equals to 1. Okay, so I'm going to draw the parabola. So theta equals to linspace 0 to pi, and x is cosine theta, and y is square root of 2 times sine theta. Okay, and right, so I'm going to graph the function of f, original function. Let's see how big should it be. So -2 to 2. Okay, and surf the I didn't define my function. So f is xy 2 times x plus y squared plus x squared, and surf xy and f of xy, and hold on to graph another one, and I'm going to draw plot 3xy and fxy, and make it as red and make it as thicker, and hold off and make it equal. So this is our picture. So you see the red one, if you project down onto the xy plane of this red line, you get this the elliptic point. So maybe I can draw it again. So maybe plot 3xy 0 sides of x, and blue line width 2. Okay, so this, when I project that down onto the xy plane, actually this graph goes below the xy plane, so this blue one actually penetrate this graph. But anyway, the red one projects down onto the blue one, which is ellipsoid, ellipse. And we're looking at not entire graph of function, we are looking at only the restriction of the function on this blue line. So that the red one is the graph of that restriction. Okay, it achieves the local maximum somewhere here, right? Somewhere here, and achieves the local minimum somewhere here, right? So obviously, by looking at these 2 points, the bigger one, okay, so let me draw again. The bigger one lies on 1,0 somewhat, and smaller one lies on -1,0. That agree with our observation by hand that 1,0 is function has 3, -1,0 has function value -1, so it should be local minimum and maximum. That's how you find the local maximum minimum on discrete constraints. So are we comfortable finding local extremals here? Because I'm trying to explain why this kind of method works. We're going to talk about the version, 3-dimensional version later, and maybe week after, next week. So here, let's try to explain why this Lagrange multiplier works. Why Lagrange multiplier works. It's a question. Let me answer the question first. No, okay, so good question. We're not finding extremal points of the graph of f. We are finding extremal points of the graph of f restricted on the level set of G. So the first question is that do we know that the extremal point of f lies on the level set of G? No. The extremal point of f may not, and mostly will not be lying on the level set of G. And we don't know that's true. The second question is that are we finding the extremal points on the constraints? Yes, we're finding the extremal points on the only constraints of the function. Okay. So basically, what we found as extremal using the Lagrange multiplier may or will not be the extremal points of the entire graph of the function. Okay. 중요하니까 다시 설명해 드릴게요. 라그랑지 멀티플라이어로 찾는 거는 이 함수의 극점을 찾는 게 아니에요. 이 함수의 정의역을 레벨셋으로 제한을 했을 때 그 제한된 영역에서 함수 값의 extremal 값을 찾는 거예요. 극점을 찾는 거라고요. 이 함수 전체의 극점을 찾는 게 아니고 이 함수 위에, 그러니까 이 레벨셋 위에 정의된 함수 값 중에서 로컬하게 가장 큰 거 혹은 로컬하게 가장 작은 거를 찾는 거예요. 자, 그러면은 원래 함수에서 극점을 어떻게 찾느냐? 그건 했잖아요. 헤세 방법으로 했잖아요. 헤시안을 찾아가지고. 그거는 이제 전체 영역에서 극점을 찾는 거고, restricted, 제한된 영역에서 찾을 때는 라그랑지 멀티플라이어를 쓴다고요. 정리가 됐죠? Okay, so here's how Lagrange multiplier, or why Lagrange multiplier works. Let's say I have a graph of function c equals to fy, and I have so in the xy plane down below we have restriction G, which is the level set of G. Okay, so on here I will have some kind of the graph of f restricted on this level set G. Okay, so let's try to think about the level set of f. So let's see. Here I'm going to take a section here, z equals to d. Okay, so level set of G will look like a circle here, because I made my graph of the function look like an oval here. So just an example. So I say that the level set will somewhere here, or it could be smaller. That's the level set of f at d. So let's focus on xy plane for now. So let's look at the xy plane again. So we have fixed constraints LCG, and if I change my level of z and try to graph the level set of f, I may have these several contour lines. So when I have d1, d2, and we have d3 here, d3, that's the level set of f. Okay. So in this case, when I change my d to be smaller and smaller, I have smaller contour lines and smaller level sets. But at some point, if we change D gradually, the level set LCF touches the level set LCG at some point, let's say x0, y0, which means that I can take nice level set with suitable this level D, such that my level set kind of touches a level this level set of G at some point. This is x0, y0. Okay. So then what happens? What does it say? So let's enlarge this picture again. So here is level set which touches the point here. Okay, that's a level set of F at D, and this is our level set of G at C. So my interest is the value of function on this graph. Okay, I'm not interested in points other than this graph, other than this line, okay, curve. However, if I move my point away from x0, y0, if I move my point away from x0, y0, then the only way I can touch or intersect this level set of F with at this point other than x0, y0 is to change my level D to larger value or smaller value of D. Okay, so you see this point is slightly touching this point. So only way so at this point, other than x0, y0, let's say x1, y1, at x0, x1, y1, the function x value at this point is smaller than D, because in order to find the value of function at this point, I need to find a level set which intersects this point at the level set of G. So if I had a level set D prime, which is where D prime is smaller than D, it could intersect point other than x0, y0, say x1 and y1, but the value D prime should be smaller than D. That's the only way I can touch. Only way I can intersect the point other than x0 and y0. So it means that in x0 and y0, the value of function is locally maximum. Okay, because if there's no other value whose function value, no other points that the function value is greater than x0 and y0, near x0, y0, all the value of function is smaller than the value of x0 and y0. Let me graph that in the MATLAB here. So that's already done here. Right, and let me draw another one. So here we have a graph of function x squared plus y squared, and on the xy plane there is a contour lines. And I will graph another functions. Let's say I want to graph this. Let's say x from let's see minus. No, so minus 1, 2. Sorry. Space minus 1, 2. Let's see. Right, well, let's use this one. It's -1 to 1, and maybe just -1 to 0. Plot of x and 1 over x as red line. And then I'm going to draw another one in space, 0 to 1, and plot x and line width as 2. That's not what I expected. Let's see. Let's fix my axis. Okay. And let's see. Maybe not using this one example then. Let's try to use the circle example. Okay, so zeta is lin space 0 to pi, and x is lambda. Let's plot cosine zeta and sine zeta as red line, line width 2. Lin space. Okay, that's not a good idea, so maybe I should use a little bit smaller ones here, or okay, let's make it smaller. Okay, that's one. That's nice. Okay, so let's say our constraints is this red ellipse. Okay, I want to find the local maximum, local minimum point of the function whose graph is like this one on this ellipse. Okay, but let's not try to graph entire graph of function restrict on this ellipse. Just look at the two-dimensional plane, xy plane. Let's say I'm going to erase this one. Erase the surf here. Look at this one. So these concentric circles are the contour lines of the graph of function. It's function graph. Let's make it bigger. Let's make it 0.5 to 0.5. So here's a contour line, and you see there are contour lines that could touch this ellipse at this point here, and here. There could be a contour line that could touch the ellipse here and here, right? These 2 points. And also there are contour line, which is smaller circle, which could touch this ellipse here and here, right? Now let's look at the value d of these contour lines. What's the option name? So let me find out the contour MATLAB contour. I want to put show text on. Okay. Okay. So these numbers are the value of the contour lines, which means that all the points lying on this smallest circle has the value of function to be equals to 0.21472, something like that, and so on. So you see, as my level increases, the size of circle increases, And so we start from the smallest one, and when I grow my level, this contour line will slightly touch these constraints at here and here, right? And when it's keep growing, it will not touch but intersect the points other than these points, the touched point, right? So, and then if it keep increasing, it will touch the point on here and here around 1, right? So what happens is, if you concentrate the points only on the point on this ellipse here, these 2 points, the top and bottom, has the smallest function value, and the left and right most point has the largest function value. Okay. So the local extremal, the local minimum and local maximum, happens when the 2 contour lines touches each other. That's the main point. So the local extremal happens when this LCG and LDF touches. What it means, or other words, tangent each other's. Okay, so what happens when these 2 curves are tangent to each other? So here's our one LCG, and let's say here is LDF. Suppose that they are tangent. That means they have common tangent line. So now we are using the proposition that we explained in the beginning. So we know that the gradient vector of G is tangent to the contour, tangent to the level set of G. And also we know that the gradient of F, sorry, it doesn't look like perpendicular. So gradient F is also perpendicular to the tangent line which touches the level set of G. Since del G are parallel to LCG, and gradient F is also parallel to LDF, and LCF and LCG and LCF are parallel. So these symbol means parallel. Thus, these 2 gradients are also parallel. Okay. So when extremal happens in the constraints, the level set of F and level set of G, which is the constraint, should be parallel, which means that the gradient vector of F and G must be parallel. So when it happens, when these 2 vectors are parallel, this G and F are constant multiple of each others. So that means the lambda is the constant. Thus, this F is lambda gradient G. For example, I think it's sometimes you can also use G. Gradient G is lambda times gradient f. Doesn't matter because we assume that this gradient f or gradient g is not 0. Okay. So what happens if one of the gradient becomes 0? We don't know. This Lagrange multiplier doesn't work. So we are always assuming that this gradient of f and g does not become 0. That in the sense that the point whose gradient is 0 vector is called a singular point. At the singular point, anything can happen. So we have no deterministic way to determine the local extremal of the singular point. So don't worry about when gradient vectors are 0 vectors. Just use the fact that these two gradient vectors are parallel. Okay. So far we talked about the Lagrange multiplier and the second is two variable function. You can use an application like this one. We'll do this later. And also there are version in three variable function. So if you know the Lagrange multiplier on three variable function, you can use this you can solve this kind of problem. If you can do this by yourself, it could be very nice, but you can wait until the week after next week. So you have a graph given by this implicit equation. I want to find the point who's closest to the origin, which means that I want to minimize x squared, y squared, z squared. Okay, so that's our target function. Say this is f, x, y, z. That's target function. What's the constraints? This is constraints. And what is our g? This is our g, whose constraints are given by implicit equation. Okay. So the situation is similar to the two variable function case. We have target function and we have constraint. I want to find a local minimum or local maximum, local extremal of the function restricted on the constraints, not on the entire plane. Okay. So that will be covered in week after next week. All right, so we don't have much problem, but these are the most important problems that we can get from the Lagrange multiplier and Hessians. So think about the problem again. And next week, so we're going to finish lecture here. Have a nice weekend, and we will see you on 2 weeks later.